Welcome to the second video lecture for the fourth week of the MPP Calculus course. This lecture is about functional analysis. It's really a continuation of the lecture from last time. So basically everything we talked about last week with functional analysis was what you could learn based on the first derivative. What we're talking about today is what you can learn based on the second derivative. This lecture will teach you how to do the additional things. I had that list of things that you need to know how to do when you see a function. This is the second half of that list. So the first thing that is useful that you can learn from a function is its convexity or concavity. I want to warn you a little bit about language. Unfortunately, if you're asked to find the concavity of a function, the answer over a particular range, the answer will be either convex or concave. That's just how the words are used, unfortunately. So a function is convex when it has a positive second derivative. It is concave when it has a negative second derivative. In terms of terminology, there's some alternate terminology sometimes here used. So convex functions are sometimes also called concave up. I find that a little easier to remember just because the shape of a convex function is a U shape. The shape of a concave function looks like an upside down U or a lowercase n. And so you understand now why we would call convex portions of the function concave up versus concave portions of the function concave down. Sometimes it's easier to think about these ideas just looking at a graph. So here we have a function split into four different regions. Notice that its first derivative is negative in regions 1 and 2 because the function is decreasing over those regions. But notice that the shape of the function really changes between region 1 and region 2. In region 1, it looks like the letter N, and its second derivative would be negative. So this is a concave function in region 1, versus in region 2 it looks like the left side of the letter U. It has a positive second derivative, so it is convex. Notice that that convexity continues into region 3. So while in region 3 the first derivative becomes positive, the function begins to slope upward, the second derivative is still positive. So the shape looks like the right-hand side of the letter U, versus in region 4, the function is still increasing, the first derivative is still positive, but the second derivative has switched to being negative, and so the graph now looks like the left side of the lowercase letter n. To think about the dividing spaces between region 1 and 2, and again between region 3 and 4, we call these inflection points. Inflection points are anywhere where the function switches from either concave to convex or from convex to concave. Now, if we think about those 2 points, the point between region 1 and 2 and the point between region 3 and 4, notice that between those 2 points, the sign of the second derivative changes. Now, what that means is that the second derivative must be 0 exactly at the inflection point. Unfortunately, if we want a test for an inflection point, it is not enough to know that the second derivative is 0, or sometimes you can also switch concavity to convexity or vice versa if the second derivative is undefined. So if you're looking for inflection points, you look for all of those places. However, that is a necessary, not a sufficient condition for an inflection point. So once you have found those points, unfortunately, the only thing you can do at that moment, is to pick 2 test points, one on either side of the potential inflection point, and check whether or not the second derivative changes signs. If the second derivative changes signs from the left to the right of the potential inflection point, it is actually an inflection point. So let's go ahead and do a quick example. Here we have the function f of x is x to the 4th. So you're going to take the first derivative. You get 4x cubed. To look for an inflection point, you're going to take the second derivative. You get 12x squared. So now you ask yourself, where is the second derivative either equals 0 or undefined? Well, this is a polynomial. There's no place where it's undefined, and it's equal to 0 if x is equal to 0. So now we need to take two test points to either side of the potential inflection point. I'm going to pick -1 and +1 just because they're really easy to plug into this function. So I plug -1 into 12x squared. I get positive 12. I plug a +1 into 12x squared, and I get positive 12. So notice that the sign is positive on either side of x equals 0. What that means is that 0 is not an inflection point because the sign on the second derivative did not change. Go ahead and try this example now on your own. Work it through, pause the video. So we take the first derivative, we get 3x squared. We take the second derivative, we get 6x. We now need to check where it's either undefined or equal to 0. There's nowhere it's undefined. It's equal to 0 when x is equal to 0. So we will pick two test points on either side of the potential inflection point. Again, I'll choose 1 and -1 just because they're easy. I look at my second derivative. There it is 6 and -6, so the sign does change. So what that means is that 0, 0 is an inflection point because the sign of the second derivative has changed. Here's another example for you to try. Go ahead and pause the video. So go ahead and take the first derivative here. We get 3x squared minus 6x minus 24. We'll take the second derivative. We get 6x minus 6, and we notice that the 6 nicely factors out so that I get x minus 1, which makes it really easy to conclude that the second derivative is equal to 0 when x equals 1. Now for this example, I'm going to also determine the convexity and concavity. And to do that, it's fairly straightforward, very similar to what we did when we were looking for local minima and maxima. I check that my potential inflection point is in the domain of the function. It is, because this is a polynomial. It's defined on the full real line. And then I make myself a little table. I'm going to look at the interval -∞ to 1 and 1 to +∞. I'm going to determine the sign of the second derivative by plugging a test point into the second derivative. So the easiest test point to the left of x equals 1 is probably x equals 0. And I would get a negative second derivative, -6. To the right of the potential inflection point, I might choose x equals 2, so 2 minus 1 is +1, I get +6. So I've verified that it is in fact an inflection point, that to the left the second derivative is negative. So from that I can conclude that the function is concave to the left, and it is convex to the right because the second derivative was positive. So you make yourself just a little table like that as you're working the problem. So here's another example for you to try. Try the cube root of x. Pause the video. In this case, you want to look for both convexity, concavity, and make a little table like we did here. All right, so we take the first derivative, we get 1/3 x to the -2/3. We take the second derivative, we get -2/9 times x to the -5/3. So that it's easier to interpret, I go ahead and write the negative exponent so that I remember that it's in the denominator. So I'm going to look at where the second derivative is either equal to 0 or undefined. Here, it's never equal to 0, but it is undefined when x is equal to 0. So I'm going to look at 0 as a potential inflection point. I need to look for test points to the left and to the right and see what the sign on the second derivative is to the left and to the right of x equals 0. Well, when x is to the left of x equals 0, x is negative. And as I look at the term Basically, I have a negative sign on the entire second derivative. It's negative 2/9, and then a negative inside the x to the 5/3, which is negative times a negative, so I get a positive number, which implies that the function is convex to the left. I check values to the right. I have, say, x equals 1. Well, the negative sign in the front times a bunch of positive stuff gives me a negative second derivative. So the second derivative is negative, implies that the function is concave to the right of 0, and that 0 is, in fact, an inflection point. We talked in class last time about the fact that you can, in fact, use the second derivative test when you're looking for local minima and maxima. The thing about the second derivative, so this is just one more piece of information that you can get from the second derivative. The second derivative is one way that you can tell whether a critical point that you have is a local minima or a local maximum. So if you have this critical point and you take the second derivative and the second derivative is positive, you can at that point, you can conclude that it is a local minimum. At that point, if the second derivative is negative, you can conclude that it is a local maximum. And you can go ahead and just draw a little picture for yourself that if x is greater than 0, it's going to be a convex function. It's going to be the U shape pointing up, versus if the second derivative is less than 0, it's going to be concave. It's going to make the lowercase letter n, so that would make it a local maximum. The problem with the second derivative test is that unlike the first derivative test, it is not universal. So when the second derivative is equal to 0, it doesn't tell you a single thing. And for points when the first derivative is undefined rather than equal to 0, it doesn't tell you a thing. So just be aware that under those circumstances, you need to use the process we talked about last week of picking test points to either side of the critical point that you're interested in. All right, other things that you can learn about the shape of a function. Vertical asymptotes, you talked about them in math camp, so I'm going to assume that you understand what an asymptote looks like, and it's just a question of understanding how you find them. Well, vertical asymptotes happen in, for our purposes, first in rational functions. So anytime you have a function that is a function of x, that's basically a fraction that has an x in the denominator, you're going to want to look for what values of x make that denominator equal to 0. If you have a logarithmic function, you're going to look for what values of x make the term inside of the logarithm 0. In either case, what you want to look at to tell if there is a vertical asymptote when that happens, you're going to test whether the limit of the function goes to positive or negative infinity at that particular value of x. Now, I'm going to say right now, I promised at the beginning I wasn't going to make you do lots of complicated limits. However, the limits that I will give you when looking at vertical asymptotes will be the kind of limit that you can work out in a very straightforward way. You can use logic to work out. You don't need to apply L'Hopital's rule or any of the other more complex approaches to limits. So I'll go ahead and walk you through this particular example. We have a rational function, so it's a fraction that has an x in the denominator. I'm going to ask, when is that denominator equal to 0? Well, that's going to happen when x is equal to 1. And then I'm going to take both the right and the left-hand limits of that function as x approaches -1. So really what you need to do here is ask what would be happening to the function as you put a -1 in place. So in terms of the distinction between left and right hand limits, I want you to think about approaching the value of -1 from the to the left, so from the negative side of the number line. As you approach -1, you're getting closer and closer to 0 in the denominator, But if if x is less than -1, that means that the term in the denominator is going to be an extremely small number that is negative. So what that means is that when you take the limit, you're going to get an extremely small number and we have to check the numerator here. The numerator, when x is -1, is going to be +3, so we're fine. This is going to approach -infinity. Compare that to the limit when you approach from the positive side of the number line. So you're dealing with a number that is close to -1, but just a little bit less negative. So something like -0.9999999. The numerator is positive. -0.99999 plus 1 is still a positive number. So what that means is that when you approach the critical or the value of -1 from the positive side of the number line, you get a positive infinity. What that means, since both of these limits are going to infinity, you have a vertical asymptote at x equals -1. As the graph comes in from the left, it will slope downward very steeply towards infinity at -1, and then suddenly restart at positive infinity and continue downwards from there. So here's another example. Go ahead and try it on your own. Pause the video. All right, so for logarithmic functions, we need to ask, when is the expression inside of the logarithm going to be equal to 0? Here we solve, we get that x is equal to 3/2. We look at the domain of the function and we realize that the domain of the function, remember that the thing in the logarithm can only be positive, so it's going to start at x equals 3/2 and go all the way to positive infinity. What that means is that we only need to worry about the limit as we come into the value 3/2 from the positive side of the number line. If you look at this particular function and you ask what is happening to the function as this gets closer and closer to 0, well, the logarithm of something really close to 0 is approaching positive infinity. That's a fact that I want you to simply memorize, that the limit of a logarithm as you approach the value inside the logarithm going to 0 is going to be positive infinity. Just memorize it. So what you can conclude then is that there is a vertical asymptote at x equals 3/2, that as the function approaches 3/2 from the positive side of the number line, it is going upwards to positive infinity. Now, at the beginning of this class, I promised we would not be doing any very intensive limits. There are some limits that you have to do for this class, obviously, for the vertical asymptotes. For horizontal asymptotes, I'm going to go ahead and promise that I will not test these explicitly, but there could be bonus points on the exam for finding a horizontal asymptote if it exists. The limits, again, that you'll have to take will be the kinds of limits that you can logic out, or that in this case you use L'Hopital's rule to solve. So here's how you check for horizontal asymptotes. You're going to look in rational functions for whether or not there is a horizontal asymptote. There will be a horizontal asymptote if either it approaches a constant as the value of x goes to positive infinity, and or it approaches a constant, it goes to a constant as x approaches negative infinity. So how do you know whether it approaches a constant? Sometimes you can just logic it out. If you have 1 over infinity, that is approaching a constant 0. If you have 5 plus 1 over infinity, that is approaching a constant 5. If you have 5 plus 1 over negative infinity, that is also approaching the constant 5. Sometimes it's going to be helpful to use L'Hopital's rule in this case. So if you, the beautiful thing about L'Hopital's rule is what it says is that if you have a limit of one function over another function, the value of that limit is identical to the value of the limit of the ratio of the first derivatives. So let's go ahead and look at an example of this. If we take the first derivative of the numerator, we get negative 3. If we take the first derivative of the denominator, we get positive 2. So what that means is that the limit of f of x is going to be equal to the limit of negative 3 halves, which of course is simply negative 3 halves. So there is a horizontal asymptote at y equals negative 3 halves. Like I said, this is not going to be formally tested, but if I give you a rational function to graph, there may be a bonus point or two for finding the horizontal asymptotes. The last part of this lecture is about sketching graphs. When you sketch a graph, there is basically a process to go through. You always need to find the domain of the function, check for the x and the y intercepts, check and draw any vertical asymptotes if you have a rational or a logarithmic function, bonus points for checking and drawing horizontal asymptotes if you have a rational function. You're going to find the first and the second derivative, and off of the first and second derivative, find critical values, find critical points, find the local minimum and maximum, and find all of the increasing and decreasing regions. So that's basically everything from last week. And then everything from this week, find all the inflection points, find the different regions where the function is convex and concave. The last step, you're going to plot each of the points. You're going to sketch a graph between the points using that information you found about increasing, decreasing, convex, concave, and making sure that you keep track of any asymptotes that you've found. So let's look at this function, 1 over x plus 3. The domain of the function is the full reals except where the denominator is equal to 0 when x is equal to negative 3. There is no value of x that makes the function 0, so there is no x-intercept, but there is a y-intercept. To find the y-intercept, we plug x equals 0. We get that f of x is equal to 1/3, so that's your y-intercept. We check for asymptotes. We look what happens to the function as it approaches negative 3 from either side. We get that it goes to negative infinity as it approaches from the negative side of the number line, and that it goes to positive infinity as it approaches from the positive side of the number line. So there is a vertical asymptote at x equals negative 3. That one point, and the way that we knew to look for that was because the derivative is undefined. We look for any horizontal asymptotes by checking the limit as the function, or as x approaches negative infinity and positive infinity. We get, as you look at this, the limit of the function. If you imagine plugging negative infinity into the function, this function approaches 0 as the denominator gets super huge. And from the negative side, it also approaches 0 as the denominator gets super huge. So we have a vertical asymptote at x equals negative 3 and a horizontal asymptote at y equals 0. We now check the first and the second derivative. The first derivative, we bring down the negative 1. We are left with negative 2. The derivative of x plus 3 is 1. So we get negative 1 over x plus 3 squared. For the second derivative, we bring down the negative 2. The negative signs cancel. We get 2 times 1 over x plus 3 cubed. Chain ruling, the inside term has the derivative of 1. So we're done. So we look for critical values. The first derivative is undefined at x equals -3, but we already know that's an asymptote, so it can't be a critical point for a minimum or a maximum. The inflection points, again, f of x, or the second derivative is undefined at x equals -3. So I need to check whether what's going on with its convexity or concavity to the left and to the right. So I'm going to pick two test points. I'm going to do my best to make them easy points to calculate. So I'll pick x equals -4 because that makes the denominator equal to negative, or the term in the denominator, x plus 3 equal to -1. I cube that, it's still negative. I get that the second derivative is negative. So I have a concave function over the region -infinity to -3. I'm then going to pick a point to the right. I'll pick -2, again, because it makes the term in the denominator equal to 1. I cube that. It remains positive. The second derivative doesn't have a negative sign in front, so the second derivative is positive. What that means is that the function is convex to the right of the asymptote. And like I said before, concave to the left of the asymptote. Go ahead right now, pause the video, and based on the information we've calculated, check and see if you can sketch the graph on your own. So using the information that we had found, we know that the function is concave to the left of a vertical asymptote, -3, and that it is convex to the right, and that it has a horizontal asymptote at y equals 0. And so the graph that we would draw would be this vertical line. Vertical line showing the asymptote at x equals -3. We should have a label on the horizontal asymptote at y equals 0. We should also have a label on the y-intercept of y equals 1/3. So here's another example. Why don't you go ahead and pause the video, try it on your own. All right, so I'm going to do this more or less in the order suggested by the slide. It doesn't really matter what order you go in as long as you do all of the steps. So I check the domain. In this case, it's a polynomial. The domain will be the full real line. If the domain's the full real line, I can basically forget about the domain for the rest of this problem. We're really checking it to make sure that there aren't any values of x that we shouldn't be graphing, and so forth. So the next thing I need to do is I look for the x and the y-intercepts. The y-intercept is the easiest to find. It just involves plugging in 0 for x. So the y-intercept is going to be the value of the function when x is equal to 0. So that's going to be 0 minus 3 times 0 is 0 plus 2. So that means that I have a y-intercept at x equals 0, y equals 2. To find the y-intercept, I need to check the roots of the function. And remember, from algebra, there are 3 different ways to get the roots of a function. You can factor it by hand, you can use the quadratic formula, or you can complete the square. Any of those is fine. I always try to hand factor it just to see if I can do that. So in this case, the first term is just x squared, so the only way to get that is x times x. The constant term is 2, so the only way to get that is either positive 2 times positive 1 or negative 2 times negative 1. So I'm going to think through those two options and whether either of them, when they add together, would give me this -3 term. And I say yes, absolutely. But if both of them are negative, when I FOIL this thing out, I will have a -2x term and a -1x term, which will add together to give me this -3x term. So solving when that is equal to 0, I get x equals 1 and x equals 2. So I have x-intercepts of 1, 0 and of 2, 0. So I'm going to just hold those in my back pocket, realize that I need my graph to go through all 3 of these points. I'm next going to check for vertical asymptotes. Remember that the way to check for vertical asymptotes is to just check what kind of function it is and then see if there are any places that make it go to infinity. In this case, this is neither a logarithmic nor a rational function. It's a simple polynomial, so there are not going to be any vertical asymptotes. I think about horizontal asymptotes. It's not a rational function. There aren't going to be any of those either. The next step is going to be to take the first and the second derivatives with respect to x. So I take the first derivative here. I get 2x minus 3. And then I take the second derivative and I get positive 2. Now, the first thing that this positive 2 is telling me is that this is always going to have the same concavity. Specifically, it's going to be convex at every point. So this function is always convex or concave up. Notice that little obnoxious bit of terminology. When I say concavity, the concavity can be either concave or convex. Sorry, that's just how the world works. What that also means is that any point that I identify using this second derivative, using this first derivative as a local min or max, it has to be a local min because the shape of this graph is going to be up like that. So I'm now going to ask, when does this first derivative equal to 0? I move the 3 to the other side. I get 3 on the other side. I divide both sides by 2, and I get that x is equal to 3/2 when the first derivative is equal to 0. I need to know the y value in order to graph it. So I'm going to plug in the value of 3/2 into my function. I get 3/2 squared minus 3 times 3/2 plus 2, which is equal to 9/4 minus 9/2 plus 2. Notice that this leaves us 9/4, a negative 9/4, so that's equal to 2 minus 9/4. And I'm going to rewrite this 2 as 8/4, okay? So that when I subtract, I get negative 1/4, which means that I have a local min at 3/2 negative 1/4. All right, so now I'm going to go ahead and, using the information that we just calculated, draw the graph. So I give myself plenty of space to work. I know that I have an intercept at x equals 0, y equals 2, so I'm going to mark that point 0, 2. I know that I have an x-intercept at 1, 0, and I'm starting to think about the shape of this graph a little bit. Notice that my next x point that I care about, just moving along the line, is this local min. So when I label this, I'm just going to be careful and label it over off to the side like that. My other x-intercept, I'm going to label off to the side like that. And my minimum point, 3/2, negative 1/4, is labeled there. Now notice the spacing on my graph isn't really perfect. If I wanted to come back, I could, erase a little bit here and try and scoot the point up a little bit. That's just fine if you do that on an exam. If you realize that your spacing isn't quite right, you can erase it. This is a reason to bring a pencil. And the reason that I did that is that I saw that here I was marking negative 1/4 at almost the same height as positive 2, which just wasn't right. If I was being really picky, I would make it higher up, but that's not really strictly necessary if you've labeled all of the points correctly and you have them more or less in the correct order. And then it's simply a matter of connecting the dots and so forth. So as long as you have all of the points correctly identified and labeled, you then just need to sketch the graph correctly, specifically making sure that you show the convexity or concavity correctly. Notice that this is a parabola, so that process that we used here, you could have used some of the things you know from algebra, like the vertex equation, and that would have worked just fine in this particular case. So let's go ahead, we'll do one more example that you can try on your own. So go ahead and pause the video now and give this a try on your own, and we'll come back. Okay, so the first thing you should have noticed about this function is that you can easily factor out an x cubed term and be left with x cubed times x minus 4. All right, so we check the domain. The domain is the full real line. We're going to check the x and the y intercepts. Notice that when x equals 0, this function has a value of 0, so we know that our graph needs to go through 0, 0. We're now going to look for the roots, what makes this function equal to 0. We've already found one of the roots, that when x is equal to 0, and the other root is apparent from this factoring. It's going to be when x is equal to 4, that will make this expression here equal to 0, making the full expression equal to 0. So we have our x and our y intercepts at this point. We're now going to look for any asymptotes. This is not a rational or a logarithmic function, so we're okay. We won't have any asymptotes. I'm going to now take the first and the second derivatives. The first derivative here is going to be equal to 4x cubed minus 12x squared. Notice that I'm taking the derivative off of the unfactored form because it's a lot easier to take the derivative just using a bunch of power rules in sequence. The second derivative I'm going to take off of the first derivative I already calculated is going to be equal to 12x squared minus 24x. So now I'm going to look for critical points, in other words, places where this derivative is equal to 0. So to do that, I factor out a 4x squared times x minus 3. So that gives me critical values at x equals 0 and x equals 3. I check whether they're critical points. The function is defined at those places. So that means that I have critical points at both critical value. And we'll come back to that in a second. I now look for any inflection points. So I'm going to look for any places where the second derivative is either not defined or is equal to 0. So here I'm going to notice that I can factor a 12x out, and I'm left with x minus 2. So that means that I might have an inflection point at either x equals 0 or at x equals 2. So now I need to ask whether or not either of those are inflection points. And notice that the order here is not super important in terms of whether you're checking concavity first, if you're looking for local minimum or local maxima first. I'm going to, just as an example, use the second derivative test to decide whether or not, or just to check whether or not these are local mins or local maxes. So when x is equal to 0, notice that my second derivative is also equal to 0. So the second derivative test does not work in that case. When x is equal to 3, I'm going to check the value of the second derivative. So I have the second derivative's value when x is equal to 3 is going to be 12 times 9 minus 24 times 3. And notice that I could also do this in the factored form where I have 12 times 3 times 3 minus 2. The reason that I point that out is this 3 minus 2 is positive, and these other terms are also positive. So what that means is that the second derivative is greater than 0. So therefore, I can conclude that that when x is equal to 3, I have a local minimum. I now need to think a little bit farther about x equals 0. It may be a minimum or maximum. It may be an inflection point. I don't know yet. So I'm going to just test the value of the first derivative on either side. On either side of x equals 0. So when x is equal, I'm just going to pick 2 points. When x is equal to 1, I'm going to look at the derivative, the first derivative's value at x equals 1. I get 4 times 1 minus 3 is negative 2, so that's less than 0. And I'm going to look at the derivative when x is equal to negative 1. Again, these test points, it doesn't matter what their values are, and I'm just picking things that make it easy to calculate. So here I have 4, and I have negative 1 minus 3 is negative 4, which is also less than 0. So x equals 0 is not a local min or max. Okay, I can cross that off. It may be an inflection point. So now what I need to do is I need to test the value of the first derivative, or sorry, of the second derivative on either side of these possible inflection points. So I'm going to again pick 2 test values on either side. So I'm going to pick the value x equals negative 1, again, because it's super easy to calculate. So I have 12 times negative 1 times negative 1 minus 2. I have 2 negatives multiplied together. That gives me a positive, so that's greater than 0. I take the second derivative at 1. I have 12 times 1 times 1 minus 2 is negative 1. Sorry, so that is less than 0. So in other words, the convexity does change, and this is an inflection point. Okay, I have already checked to the left of the other possible inflection point, x equals 2. So now I'm just going to check something to the right of that. I will choose the value of the second derivative when x equals 3. So I have 12 times 3 minus 2 is positive 1, and that is going to be greater than 0. So this is also an inflection point because the sign of the second derivative changes from one side to the next. So if you were actually doing this problem on a large sheet of paper rather than a tiny computer screen, as you were working through the problem, you would have been creating a table that looked something like this. So notice that I have the first derivative. I've figured out, basically I've signed it continuously. The last thing at this point that's left to do is to figure out the x values where for the points that I've not yet calculated. Or sorry, the y values for the points that I've not yet calculated. So I'm set for the 2 intercepts, obviously. I need to figure out what the function is equal to when x is equal to 3. So I calculate that out. I get f of 3 is equal to 3 to the 4th minus 4 times 3 cubed, which is equal to 81. So I usually think of this in my head as 3 squared is 9, 9 squared is 81, and 3 squared is 9, 9 times 3 is 27, so it's minus 4 times 27. This is also a moment when the alternate expression could have been useful, so if I knew, I could have just written that x cubed is 27, and that 3 minus 4 is negative 1, so that's simply negative 27. So that means that I have a minimum value at, just to write it as an ordered pair, 327. My inflection points, the first one I already know that its y value is equal to 0, so I have 0, 0. The second one I need to calculate, and based on the positive experience doing it last time, I'm going to use this alternate form of the expression. If I take, just searching for space here, the value of the function when x is equal to 2, 2 cubed is 8, times 2 minus 4 is negative 2. So the value here would be negative 16, and I have an inflection point again at 2, negative 16. So all that's left at this point is to actually sketch the graph. So I'm going to use the insight that I have from all of these different points. I have this point at 0, 0 that I'm going to care about. I'm going to be pretty parsimonious with my y-axis space because I need to get all the way down to negative 27. So I'm going to put negative 2, 2 negative 16 right there. And I'm going to come a little bit farther down and get negative 27, 3. Notice that, you might erase that if you want to. Just be a little bit careful about the spacing when you have any control over it. Okay, so maybe that line should have been right there. Whatever. That's fine. That's a 2. And now I also know that I have my intercept out here at x equals 4. So I look at at all of the different points that I have, and I look at what each of the derivatives is doing. So at 0, 0, I have a function that's coming in, and it is decreasing but concave up. So the shape coming in looks a little bit like that. And I usually in pencil just kind of sketch the shape right on the inflection point I'm going to be thinking about. And then coming in the on the right side of the inflection point, I have something that is concave down and also decreasing. So it's going to do something like that. I look at my other inflection point at 2, negative 16. We've already said coming in, it's concave down and decreasing. It looks like that. On the other side of the inflection point, it continues to be decreasing, looking at the first derivative, but it goes back to being concave up. So I draw it like that. I do not have any other inflection points. I know that I'm going to here have a local minimum. So before I actually sketch the full graph itself, I usually check each of those key points. And then this last point is just an intercept that I need to respect. So to finally connect all of the points, I'm drawing something coming in roughly concave up, switching it to concave down, making it concave up again, making it a minimum, and then just increasing from there. And that would be your graph. Just like with anything else, these are the kinds of problems where it's really important to simply label your work, which it's a little harder to see, but making a table like this is always a good idea. Labeling things, your inflection points and your minimum points and your intercepts is always a good idea. And with that, we are at the end of the second lecture for the 4th week of the MPP Calculus class. I'll see you in class on Monday.